We all tend to hold this really common belief about modern, highly optimized systems. We assume that global supply chains, massive data networks, and complex manufacturing pipelines are designed purely for speed and continuous flow. The ultimate goal, we think, is absolutely zero friction, just a perfectly smooth operation. But if you actually stop and observe the most optimized networks on Earth, you immediately run into this glaring structural contradiction. The very systems that are the most desperate for speed intentionally force themselves to hold massive, completely idle reserves. And this intentional delay, it produces some immediately disturbing consequences. We're talking billions of dollars in trapped capital, delayed network packets, and stagnant materials just sitting untouched in sprawling million-square-foot warehouses. The system is literally building friction on purpose. There is something unseen going on here, something structural that is forcing this behavior. Imagine a really simple physical system for a second. Picture a constant flow of water pouring into a large holding tank. Now, at the very bottom of this tank is a release valve, and this valve is significantly narrower than the intake pipe. Because of that, the water is forced to pool in the tank before it can squeeze through that narrow exit. So what happens? The water level rises relentlessly. It just sits there, doing absolutely nothing but waiting. Now, to an outside observer, this looks like a major flaw, right? A massive inefficiency. But this rising mass of idle water is not a mistake. It's actually a structural necessity for the system to function at all. Let's dive into Section 1, the mathematics of delay. What actually happens if we try to just remove that holding tank entirely? What if we force the water to run at 100% continuous flow, matching the input perfectly to the output? Well, in a theoretical, perfectly rigid world, continuous flow works beautifully. But in reality, arrival and departure rates naturally vary. Sometimes the water surges, and sometimes it's just a trickle. If we remove the tank and run the system at full capacity without a place for the water to wait, these natural variances instantly collide. When a surge hits a narrow pipe with absolutely no room to expand, the flow doesn't just slow down, it violently stalls. And as the queue length grows indefinitely, the actual output of your entire system just plummets. We see this exact behavior across all complex infrastructures. When digital communications try to run at their maximum theoretical throughput without a buffer, they don't just run slightly slower, they drop data packets catastrophically. Or think of an automotive factory. If you remove all the intermediate parts waiting between assembly stations, a single 5-second machine delay halts the entire mile-long facility. A system literally cannot exist without creating its own delay. So let's go back to our physical tank. The water is filling higher and higher. The static pressure is building heavily against the glass. Yet the system is perfectly executing a mathematical necessity. It isn't experiencing a failure at all. It is simply surviving the only way its physical structure allows. Which brings us to Section 2, the illusion of stability. As this physical mass grows, the system actually begins to mask its own underlying volatility. It absorbs all these external shocks to maintain what looks like total stability. Consider a chemical pH buffer for a moment. If you drop strong acid into this solution, the pH doesn't just immediately plummet. Instead, the buffer molecules react, quietly absorbing the excess hydrogen ions. The chemical shock is completely swallowed. The volatility is hidden away, and to the naked eye, the solution appears perfectly stable. This chemical absorption is exactly what physical systems are doing when they build vast reserves. In global supply chains and retail networks, we observe this as safety stock or pipeline inventory. When a massive shipping route is delayed or a supplier completely misses a deadline, the end consumer doesn't feel it at all. The safety stock absorbs the shock. The idle material is consumed instead, totally hiding the systemic disruption from view. But remember, this stability is an illusion. While the surface remains perfectly smooth, the internal pressure is mounting fast. That chemical buffer is nearing its absolute mathematical capacity, and if you add just one more drop of acid, the pH will collapse violently. In our physical tank, the water level is inching dangerously close to the brim. The system is absorbing shocks, yes, but it's doing so by endlessly growing its own volume. Moving into Section 3, the structural trap. We've now crossed a dangerous threshold. We are forced to look at the hidden structural constraints that the system has been quietly building this whole time. You might be wondering, why can't the release valve simply be widened? Well, because every system has a limitation point. We call this a bottleneck. It's a single process whose limited capacity strictly dictates the maximum speed of the entire chain. If the bottleneck ever runs dry, the whole system loses output that can never ever be recovered. So, to protect this narrow valve from ever starving, the system is forced to provide a constant, massive buffer stock directly upstream. Keeping that bottleneck running at 100% capacity means the entire surrounding architecture has to permanently change its behavior. The system is no longer organized around delivering the final product. It is now strictly organized around managing the accumulated idle mass waiting at the bottleneck. And this continuous accumulation triggers severe secondary constraints. The water tank suddenly needs thicker walls and stronger supports. In our real-world systems, this translates to sprawling physical warehouse space, massive insurance premiums, and crushing network protocol overhead just to maintain the queues. The system is spending vast amounts of its own energy simply holding on to things that are doing nothing. The holding costs required to manage this mass can quietly consume up to a third of the inventory's total value every single year. Meanwhile, the actual useful output of the network plummets. The system is now consuming resources just to prevent its own safety mechanisms from collapsing under their own weight. Now for our final section, total system lock-in. We escalate to the final stage here. The physical tank has grown so massive, so incredibly heavy, that the structural pipes supporting it are literally groaning under the static pressure. Escape is no longer an option. Look at the water at the very bottom of the tank. It's been sitting there so long that it's become completely stagnant. In our global supply chains, this manifests as distressed inventory. We're talking about materials that are obsolete, expired, and absolutely impossible to move. The very bottom of the buffer is dead weight, permanently trapped by the new flow passing continuously above it. The system is now entirely locked in. It's crippled by the sheer weight of the exact mechanisms it rationally built to ensure its own speed and survival in the first place. It can't reduce the buffer because the bottleneck would immediately starve, and it can't increase the flow because the holding cost would crush it. It is entirely paralyzed by its own safety. When we observe these global slowdowns, the gridlocked ports, and the heavily congested data networks, it is deeply natural to look for a broken machine, an error in the code, or just a person making bad decisions. We always look for something to fix. But there is no one to blame here. There is no error. The delay isn't a malfunction. The massive, immovable weight slowing everything down is simply the system perfectly executing its underlying mathematical logic. The system was never failing. It was following its structure. So the next time you find yourself frustrated by a delayed package or a seemingly irrational network gridlock, ask yourself, is the system truly broken, or is it working exactly the way it was forced to be designed?